is, where do I have my, no, not that one, this one. If we have magnetic monopoles, it means that it has to be here. Magnetic monopole would create divergence of magnetic field. Well, but those are so special that at least we have not yet really found at least very, very clear examples of that. And that is in a way very important thing. I mean, big applications to the magnetic field. You know that Earth has a permanent, constant magnetic field which turns our compasses, goes to the North Pole or close to the North Pole. And then if we had a magnetic monopole, what happens to the magnetic monopole? The magnetic field is creating a force to the magnetic monopole, and it would go towards the North Pole. And that is an excellent idea for the postal office. You know, if you have a letter, would like to send it to the Eskimos in Greenland, write the letter, put it into the balloon, and one magnetic monopole. It goes to the Eskimos. That is perhaps the reason why there are no magnetic monopoles. Everything has migrated to the magnetic North Pole already. So you can see that this is a stable, unstable situation. Okay. Any questions? By the way, the Maxwell's equations, have you been used to seeing those in this form or some other form? There are many other forms also in Maxwell's equations. But perhaps, yeah, right.
Yeah, no, I thought I remember them with constants in front of the dv by dt.
Ah, good point. Yes, the question is the d by dt. Yes, now we come to this one. So, of course, these are now valid for fields which have any kind of time dependence. But then we very often would like to deal with single frequency fields. Or broadband fields, but analyze those by single frequency and then make a Fourier transformation. So it helps a lot if we somehow now say that our field variation is temporally. But now let's do it like this. Sorry. So we have a, say, temporally field is going like a sinusoid. So that means that the electric field in antenna, it means that it is like in this direction, but after half a wavelength or half a time temporally, it is the other way down. It goes like this. And the important parameter is the frequency, the speed, how quickly it goes. We talk about, say, the period, so that we have the frequency, which is one of the period. So if we have a 1 microsecond period, it means a 1 megahertz frequency. And quite often we then also talk about the angular frequency, which is 2 pi times the linear frequency. Okay, hertz is the measure for frequency. Okay, so but the good thing about this kind of sinusoid is that since we have, say, sine omega t type of dependence of the field, which is the thing that then we, in the differentiation, what happens? If we take the time derivative, sine derivative is cosine. Yes? Oh, sorry, it's very, yeah, sorry. Like this. Sine derivative is cosine, but of course the time derivative, the quicker it is, the stronger the derivative. We have to multiply it by omega. You know this rule. Meaning that if we have sine, we become a cosine, but multiplied by omega. Or if we had a cosine, the differentiation is minus sine omega t, and then of course multiplied by omega. So it is about the same. Sine is nearly about the same as cosine, only a phase difference of 90 degrees. So it would be so nice if the differentiation would be exactly the same. So let's take a compromise. And this is what we do. We say that we take exponent, j omega t. Why? Well, just because of the fact that if now we differentiate, what happens? It remains the same. It doesn't change to j to...
maybe the time derivative.
Happens like this.
Time derivative.
Oh, sorry. Good. Thank you. Let's do a little bit like this, and then... it's a bit difficult to see from... Yeah, time derivative. Okay, but now it's easy because now I mean, this is not so necessary, the blue one here. Which means that the time derivative is exactly the j omega. But now the problem is, now we gain something. What did we gain? We got rid of the time dependence, because now you can see that anything that varies the original source with the sine thing there causes that all the other fields are also with the sine cosine thing. And all these are like varying with this omega sinusoid we call time harmonic variation. So we can drop. Everything has this exponent in them. We drop that. We forget about that because we know that everything is varying by this. But the problem is that we got a complex thing into our equations, meaning that now we deal with complex vectors and complex scalars. So this is a bit difficult because it means that what is a complex electric field? How can we measure that? Because what we measure with our charge is a real electric field, what the force is. But now the complexity is in a phase. We have a field variation and there is a phase. So multiplying by g means a 90-degree phase shift. So let's now come very important point, and I want to emphasize this. First, remember this one. So our notation, our deal is that we play with this kind of time, e to the plus j omega t, because many people, especially physicist-oriented people, may talk about e to the minus I omega t. And this is unfortunate. So, of course, I is the imaginary unit, imaginary unit. And j is also the imaginary unit. But in electrical engineering tradition, due to the fact that I is always refers to current, we use j. But then this means that there comes always like a change of sign in the imaginary part of the concepts. Like in the material case, it is quite annoying because that comes to the losses, and the sign of the losses is then where does the the plane wave increase in amplitude or decrease in amplitude, and this is of course very important. So please remember, and I'm afraid, may I not ask Sergei, do you remember, is Nader using this notation of a to the plus